And today we're going to talk about how to pick a vector database. And we already have a couple of questions that they're like perfect. I don't know if somebody is like trying to tee these up for me to make my job easier, but I do appreciate it. So the first question is really a simple one, Lee, and what is a vector database? And can you answer that in just 30 seconds?
Okay, I don't have a very good explanation, but vector base is for store and search, and for a database for vector search and vector store.
There we go. Perfect, simple answer. And then there's another question, which is what are the key differences between a graph database and a vector database? And we're going to answer that towards the end because we have a lot of stuff that I want to make sure that we cover. And then I think it's going to make a little more sense about what these key differences are. So instead of kind of going deep into that, we're going to try to lay the groundwork so that by the time we get to that question, it'll be super obvious. All right. This is also meant to be very interactive. So if you have questions, I will do my best to watch them. And Sachi, my friend here, is also watching them. But let's go and get started. The other thing that I want to make sure that we all recognize is that today is Pi Day. For those of you that might not be familiar with Pi Day, March 14th, 3.14, in honor of this very mysterious number. It's always interesting to me that, it's an infinite number, and yet circles are everywhere in the world. So hopefully you guys had a little bit of pie, pizza pie or apple pie or cherry pie in honor of this. And let's get started in the topic. And the approach that we're taking today is that I want to make sure that I don't want to just dictate my opinions or Lee's opinions on how you should pick a vector database. I think it's really important for us to help everybody understand what are some of the key things in a vector database that you need to consider so that it works really well with your particular use case. Everybody's a vector database nowadays. Hooray! That's so awesome. You would think that I would be a little bit upset, but actually I'm really happy that everybody is interested in vector embeddings because they are so powerful, and they've already made a pretty significant impact in our work that we do. And the more that we can learn about it, the more we can get more developers utilizing it, I think we'll be able to get a lot more insights. So that's really super great, but then it makes it confusing for a lot of you about which vector database you should consider and what are the things that you should look at. So we're going to start off with this question, which is, what are the primary use cases for vector databases? I think everybody knows what RAG is, retrieval augmented generation, but Lee's going to tell you that that's just one of many, many, many. And then Lee, also, if you can not only tell everybody what are the use cases, but what are the particular features or what are the particular requirements that people should consider with a vector database in regards to these very specific use cases?
All right, so yeah, given we get some questions about what is vector database, so I think I need to introduce some concepts here. So vector database, and we extract the data, the embedding, which is vectors from some unstructured data like graph and video, audio, this kind of things, and store in vector database, and we can search it upon another vector. So we call it similar search. And about the use cases, I say the most I can simply categorize this into two different parts. And first is the online one. So online one, the most typical one is it should be the RAG, and the hottest one. And the RAG is work with LLM model. So you need prompt and you get some relevant information stored in vector database, and combine with your query to become a prompt and get into LLM model to help large language model to understand some more information. Maybe it's private information, or it's updated information, or this kind of things. We call it RAG. And also, besides the RAG, actually RAG is the hottest topic, but besides RAG, so many other things happen inside of vector database, the online cases. For example, you do graph search, like you do, for example, you try to search some similar product in the Amazon, or you do a picture search on the Google. Basically, the behind the screens graph search happened, and behind this graph search is vector search. And this is where we should use vector database. And also some document search and fraud detection. So in fraud detection, which means that some risk, some problem, some risky happened, and some transaction maybe is very suspicious, and you need to find it out. And we cannot exactly match it with something inside our database, but with some semantic similar match. So this is a reason, this is a method how we find it out. And this is online cases. So for online cases, I will answer questions mentioned what the features we need to satisfy this this scenario. First is of course the performance, and performance is always important. No matter for what kind of database, and for online things, and maybe some of the people think that RAG doesn't matter. The performance doesn't matter for RAG because large language model is super slow. So, but we can consider that you will have so many tenants there. So you may so many users can use a large language model and then rely on a vector database. So we also need to have a very high throughput and very high performance. And the second one is about the real time, which I will call it. So the building speed is the index building speed. So how fast we can ingest data into the vector database and serve this kind of data. And that is another important thing. So for other than the performance, we have also some other features. For example, the strong scalability, since in these online services we always have a peak and valley traffic, and we need to take advantage of this. And we need to scan out and scan in and to save the money. And also since you're online, so it's very important. You can never have any problems. So fault tolerance. And so which include backup and failure resistance, all these kind of things. It's very important, just as a traditional database. And also observability, like we have monitor system and a tracing system, and also this can help us to discover the problem as fast as possible. Also the operability, I call operability, which is that when we find it out, the problem out, and we have a good design, a good tool to fix it. That is what we need to, most important features for the online cases. And for offline scenarios, we have some, for example, the data mining. So when in the machine learning build stages, you will try to find some similar data that help you to fine tune this model, or you want to tune the model or fine tune a big model, whatever. So you need to find some similar data. This a vector database can always help on that. Also, some data cleaning work. I noticed some of the large language models training process, they have tons of data and they need to dedupe them. And the deduplication is not based on some single word letter to letter match. It's about some semantic deduplication. So we need to use a vector search here as well. And the most important feature is I say the batch search performance. So it just a little bit different than the online one. We search one by one. In this case, is the offline case, we always do a super batch search. Also, some other features like the capability. So how many data you can store, because offline is always big, and some rich search semantic for analyze, like the range search, field search, and group by all this kind of traditional OLAP database. This kind of rich search semantic is also needed for a vector database.
So let's untangle that a little bit. So what you're saying is that for some of these online use cases, let's just go from the top. So like with RAG, I think there's a lot of chatter out there that says that performance doesn't matter because your LLM is super slow. But you're saying that no, actually performance does matter in the RAG use case. And so it's something that people should consider. And then also, if I heard you correctly, there are some use cases where, like the anomaly detection use case that you described, I think, having a very precise answer is really important, and having all the data presented in that results is also important, because we're trying to find that outlier, right? We're trying to find that thing that is causing that anomaly. And we want everyone to keep in mind that, a lot of what we're doing here is a lot of times we're doing what we call an approximate nearest neighbor search. But in that anomaly detection use case, we want to be able to find, what that actual thing is. And so it's really important to make sure that you can understand if your vector database has all these capabilities to get you to that outlier question. And then I think you also just mentioned some of these offline use cases. It's not just about just doing that initial search. It's about then taking that data and then and doing more, using that to further train the model. So there's so many different use cases. And in this brief moment, I think we've just heard that there's also lots of different situations, lots of different ways to search on that data. And there's also a lot of different kind of expectations that you should have on the performance of the database. Is that correct?
Yeah, so yeah, definitely. So actually, this is just a rough conclusion. So actually, we have so many different. I call it corner cases. It's not about this corner, but it's not that hot, not that popular. For example, I know some biotechnology. They also use vector search. They are doing some protein prediction, and they want to match the to find the similar protein and through vector search, because you can always transfer the protein to some letters. So from biology perspective, yeah, this kind of this is very interesting.
Yeah, actually, I just met with the user just 2 days ago that's like doing all that. And what did he say to me? He said it in such an eloquent way. He said that when you realize that proteins are a sequence of amino acids, then you start to realize that you can, these models can actually learn the protein grammar, which I didn't even think about it from that perspective. And yeah, and so in that particular case, we do want to get like, a very relevant search result in that case, because they're ultimately trying to build, a really optimal protein for a number of different kinds of use cases. And some of it could be in things like, I think he was telling me to use these proteins instead of using oils in plastics, or some of it could be in medications. It's just completely different world than just software engineering.
Yes.
Fabulous. Okay. So moving on here. So why does how a vector database handles scaling matter? Like, because I think there's we can scale up or scale out, but why does this matter? And why should we think about this? Or why should we make sure that this is important in regards to our particular use cases?
Okay, so first I want to answer. I want to just introduce a little bit of base concept. So about what I already mentioned, scaled out or scaled up. So I would call it horizontal scale or vertical scale, and about so why it's important, and definitely because data is getting more and more. So everything as I mentioned. Biology, biology company use large language model, use vector database, and some other maybe other industry work you use these large language models. And when you get into model and vector is always you cannot avoid. And when you come to vectors, and we have more and more vectors, and definitely your vector database need to scale. And about the different kind of scale method. So the horizontal scale is as simple as simply enlarge the host, make the host bigger and bigger. And the vertical means that you can add more hosts to this cluster. And horizontal scale is unlimited, since you can. Oh, so or maybe sorry, I made a mistake. So horizontal is add more host, and the vertical is make it bigger, and horizontal is unlimited, since you can add as much as you want, and the vertical is limited because it cannot a single host can never grow very, very big, right? It can never go unlimited big. And many vector database now, since our topic is about how to pick your vector database, so a little bit more about that is many vector database, most of them usually support horizontal support vertical scale. So since it's most easy way to implement, like and also in some other database like search these kind of things, and they usually also only do this vertical scale, and this can help make things easier. And when you scale it, I think the performance will be the improve the performance will be linear to how much you scale, since the overhead will be less. And the problem is that it can never grow, right? So can never grow super big. And we always support the horizontal scale. And for horizontal scale, so for the verticals, the problem is that you at the very beginning you didn't know in the future how big your data will be, how big your database will be. So if you underestimate it, you will suffer, and you'll find that, oh, it's so crowded, I cannot do any more scale.
Yeah, yeah. And I mean, it's interesting because it's, it's something that we came up with, not me, but the industry came up with, like, 20 years ago, maybe more, like the idea of horizontally scaling. And yet every time we introduce a new type of database, we fall into the same trap. We all start with a database that scales vertically, and then we realize over time, oh dear, actually the number of items that we're trying to deal with is actually really large, and now we need to figure out how to do it horizontally. So it's not a new way to address the challenges of scale. It's just that I think, with vector database, it's something that you need to think about. And when we're building prototypes, maybe we have 100,000 vectors and we think, it doesn't matter. But it's really, really easy to get to 100 million vectors. And it's really easy to get to 1 billion. Don't you think, Lee?
Yeah, and this world is changing, right? So with the model is grows so super fast within last years, and maybe at the beginning of the 2023, you will say I will have just 1 million or 2 million of data, since you didn't say the large language model, you didn't say anything. But after that, so you need tons of for nowadays, most of our use cases is about you use billion to count instead of million.
That's right. That's right. Yeah. And I think, if anybody on this session is building out a RAG solution, you're probably seeing that even as you're chunking up your text and your PDFs, that it can start to grow really quickly. And let's just do some simple math here. Let's just take an example of maybe like a medium-sized e-commerce site. There's a bunch of items that are being sold, and each item can easily have, maybe 5 pictures, a video, a bunch of user reviews, a product description. So it's really easy to see how a single item that you're selling could have 30, 50 vectors of all different kinds, right? And then multiply that by the number of items you have in the e-commerce site, and then boom, you're at 100 million, and then, or 300 million, right? It really does add up a lot quicker than I think a lot of people do realize. Okay. Actually, before we go to the next question, there's actually a good question from the audience. So is distributed computing applicable to both horizontal and vertical scaling?
Sorry, let me take a look. So yeah, of course. So when it comes to distributed computing, so this description is a little bit vague, because horizontal, no matter horizontal or vertical, both of them are distributed. So I think the answer is yes.
Yeah. It's just as Lee mentioned, like, if you're going to go up, you're going to eventually hit a ceiling. And so it may be fine depending on your use case. So once again, think about, how many vectors you think you have today and what you think you're going to have tomorrow or in a year or two. And if a vertical, scaling is good enough, then put that in your checklist of how to then determine which vector database is going to work for you. If you think you're going to get to, much larger scale, it's better to understand that and make that decision early on than having to then, try to move all these large number of vectors in your vertical scaling solution to a horizontal one. Okay, let's go on. Okay, so I think there's a lot of terms that are thrown out there that try to describe kind of like the performance and kind of the unique characteristics of vector databases. So can you describe to us, what does relevancy mean? What does scalability mean? And what does efficiency mean in the world of vector databases?
Yeah, so relevance maybe I thought it's because vector search is not a exactly search, which means that you will not get so we always say top K similar one, but maybe it's not very is exactly the top K, since you this is the reason why we have this kind of concept called relevance or recall. So because we treat this is trade off, we sacrifice some of the accuracy or relevancy, this kind of thing, to improve the performance. And this is and also because it's vector is a database behind the AI, and we have model there, so we don't need to be that exactly the same to make the model perform well. Yeah, this
Yeah.
is about the relevancy and scalability, as we just mentioned. And actually, it doesn't have any differences than the traditional database. And you about architecture, you need to scale, horizontal scale, and vertical scale, and you have shard, this kind of replica, this kind of concept, basically the same. And about efficiency, so it's if you mean some performance and cost, do you mean by this?
Yeah.
Okay, so it depends on the use cases, and we have different kinds of. So the most heavy part inside a vector database, most important part is about the index. So what different kind of index you choose? Indexes help you to do similar search, and the index will occupy most of the resources. This will affect the efficiency, affect the cost, and you can either put it into a disk, either put it into a memory, and you can quantize it, you can compress it, and this can also have different kind of efficiency. It depends on the cases, I think, depends on your use case.
That's great. So then let's just dig into relevancy a little bit more by asking the question. So what kind of search is available in a vector database? Because you mentioned that, we're trying to find something that is as close to possible, right? The top K. What does top K even mean?
Top K means that in vector search, we have some metrics to how to evaluate the similarity. We have L2, IP. L2 is just some IP and cosine, this kind of distance. And if two vectors are very close in this distance, or we call in this vector space, and we find the top K closest one from it. So this is how we call top K search. And what kind of search? So top K is we call it AN search or top K search. This is a very basic one, and actually it's more like a vector search instead of a vector database. And so many lab can do this, right? And like Face and this kind of, you don't need a database upon it. And for when it comes to database, I think we need to richer search semantic. And for example, we have filtering search. Filtering search means that since you can treat your database as your collection or your database as a MySQL table, and you have a column is a vector column, and you do a vector search upon this vector column. And also you can have other column. So it can be scalar columns, that can be string, can be int. For example, you have a picture, you have a description of it, you have a label, you have the date it get take in there. So all this data can be used as a filter for the vector search. For example, you want to find the top K closest picture, but you don't want anything involved, including a red hat maybe. So this is called filter search. And that is very important I think it's a very important search semantic inside the vector search. And also range search is also another one. Range search means that instead of use top K relevant, and we want to have some the vectors within a range, distance range. As mentioned, we have altitude, cosine, and IP as a distance metric. And some cases like you want to find a similar one, but you don't know how similar. You don't know how much you want to find it. You also feel concerned how much similar data I have here. So maybe you have just a range. So I say with the distance within 2, I think the definition is within 2, it will be very similar, and you want to get everything else. So that is a range search. So about group by search. Group by search means just like traditional database, we group by some data and get it out. For example, if you do a similar search on a Snoopy picture, you will get top. What you want to get is top 3 different kind of dog. So you will get. You hope you can get Goofy. You get some other dog. You get Snoopy. But what happened is you make 2 exactly Snoopy, because you have so many Snoopy there. So in this case, you want to say I want to group by something. So you group by the name of it. So if it's Snoopy, just give me 1. And then finally you can get Snoopy, Goofy, and some other dogs. So this is just an example. So we call it group by search. And also you can group by some vector. So instead of group by only on the scalar data, I will say the string, you can also group by on the vector, which means that if the distance is super close, you can treat it as the same. So it's another. So I will call it vectorize some semantic search, search semantic from the traditional database. Another one is iterator. So given some cases, you just like Google, you try to search some similar things, and you try next page. Basically, it's an iterator. And in vector search, also you want to have top K, top 10 to top 30, 20, top 30 to top 30, this kind of thing. So we call it iterator search. And also sparse is another topic. So since vector search is it's about semantic search, which so the model will extract the semantic information from the unstructured data and make it a dense vector, equidense vector. So and sparse, which means that you will select the vectors extracted by BM25, TF-IDF, this kind of traditional statistics based on no, it's not a model. It's about some algorithm, and you'll get a very sparse vector. And this is has more information about the keywords. It's about statistics, and actually it's a complementary to the dense one, about semantic one. One is focusing on the context on the semantic. One is focused on the keyword and then you can combine together. So finally, it's about how to hybrid this kind of two different search. And like you have multiple vector, one is sparse, one is dense, and you how to combine them together to make your search better. So also an important thing to support inside the vector database.
Yeah, and that last point, making your search results better, is going to depend on what you're trying to search for and what's in your database, right? It's not that you can't answer that question with just one way of doing a search, because you mentioned a whole bunch of different ways that we might do searches. You mentioned that, we can filter first, filter out by the scalar data or the metadata, so that basically you're trying to limit, what your population that you're going to search against. So that's the first one. You also mentioned, I think something super fundamental, which is that we're trying to find similar things. And so that's why we are getting this top K results. We're trying to find the top 5 similar items. And sometimes in your data, maybe your results are not going to be what you expected when you do that. I want to find the top 5. And so that's why you need to also consider the ability of doing what we call a range search, where you can basically put like a range around that data. So I want, within this area, I want to find the results. And the top K may be outside of that area, or maybe all inside of that area. You also mentioned group by, which I thought your example of looking for Snoopy or looking for dogs like Goofy and Snoopy, what are you really trying to find when you're doing that search? Are you trying to find just Snoopy, or are you just trying to find dogs or similar dogs to Snoopy? There's a lot of different questions that could be asked. Even the other thing I think in group by that you kind of hinted at is when you think about like a RAG solution, we're doing a semantic similarity search on the chunk of the data. And then what are we actually trying to surface? Are we trying to just surface the chunks, or we want to group by the actual PDF or the original corpus of data to say like, okay, we want to, see all the similar docs, and we're doing a search, based on the chunks. So you might want to group by that.
Yeah, very similar, similar to the traditional database. Maybe we can still have some aggregator after. So you group by the ID of the PDF, and then you want to aggregate the scores for each paragraph. You just add them together, or you just find the max one, and you do a top K on it.
Yeah, that's a really great point. Because when I first heard the word group by, first thing I thought was aggregators. So yeah, so there's a possibility of adding that aggregation as well. And then what else did you add? And then and then you mentioned so hybrid search. I think in the industry, when you look at all the vector databases, everybody has their own definition. So it's important for you to tease out, what does hybrid search mean? And hybrid search, go ahead.
Oh yes, it's just a interrupt. So sorry about that. So hybrid search actually, so for now, the most of the definition is about since a very typical recommendation system is use some Elasticsearch and vector search. Elasticsearch is some traditional statistic based search, and then vector search, and then call top K from each other together and combine the result together. Have a re-ranking model, this kind of thing to get it out. We call it hybrid search. And in our in Milva side, in data side, so we call the hybrid search like if you want to combine the result of two vectors, two columns of vectors, and then you want to combine the result, so we call it hybrid search. It can be either be a sparse and dense vector, also dense vector and dense vector. So for example, you can have a video, and you encode you embed you get the embedding from the movie, the graph, or the visual data, and then you get a column vector from the audio data, and then you can try to combine the search result to get what you want, what video you want. Example. Yeah.
That's a really great example. Yeah, and so unfortunately, when you guys are looking for a vector database, you can't just take the name of the feature at face value. So you can see hybrid search underneath is a whole bunch of different things. So as you're trying to choose these vector databases, really dig into it and figure out like, what does hybrid search mean? Is it just metadata filtering? Is it, the dense and sparse vectors? What are they actually talking about? And then make your choice based on what your feature requirements are. It's an unfortunate thing in the industry, but it's important. We want to make sure that, we highlight that. One other thing that you said at the top of this question was, when it comes to, approximate nearest neighbor search, you can just use a vector index like face, which is not a database. So how would you describe what the difference between a index and a vector database?
All right, so yeah, this is a very, very classical question. So from face is a collection of a library, and beyond that, so the relationship between face and vector, for example, Milvus, is just something like we can InnoDB and MySQL. So you have more than, or a B tree and MySQL. So you have more than that. So you have the as mentioned, the scalability, and also data persistent, for tolerance, monitoring, and yeah, all these kind of things. So because library just working on, it's just an algorithm, and comparing with algorithm and the database. So there's a lot of gap there.
I love that. B-tree and, like MySQL. That's a perfect way to describe, the difference between like a a library and index like FACE or HNSW and a vector database. So, well, I mean, and do you think that there are some situations where maybe a library is just good enough for people?
I guess so. If you are doing some experiment with more, you're in a laboratory and you work on some small amount of data, like less than 1 million, feel free just to work on a library, since you don't need, and you are not serving the production. You don't need to have this kind of fault tolerance or this kind of monitoring system or some security system. Yeah.
And so then the next question is, what's the difference between a similarity metric and a index? So like, well, how would you like describe, like, because you talked about Euclidean L2, you talked about inner product, you talked about cosine, right? Those were your similarity metrics. But then we have these libraries or indexes like HNSW and FACE, et cetera. So what's the difference between the two? All these words just sound like, a lot of confusion, right?
Distance is the metrics is just decide how close you are, and for example, so there are two vectors. It can be use IP, which means that just multiply with each dimension, add together as a distance, or you can use L2 Euclidean. And about the index, is different kind of ways. It's a data structure to form this kind of vector, and make you can search this as fast as possible. And this search, the top case search, is upon the metrics. For example, you use IP, you will search, the result will be similar in the IP perspective. If you use L2, it will be top K with under the top K perspective. So yeah, it's a two different kind of thing.
Cool. Awesome. And then when you look at your actual index building, or you building out your queries, you'll actually see that a lot of these things are requirements. And so hopefully that's going to make a lot more sense as you're learning how to use these various vector databases that are out there. Okay, let's go on. Okay. All right. So everybody talks about, oh, wow, well, we just support HNSW. So everyone knows what that acronym is now if they're in the world of vector databases. But there are so many other indexes. Is HNSW good enough? Should people know about the other ones? Are they important?
I think HNSW is famous because it is easy to get, and also it's easy to understand, and its data structure or this kind of concept is sold solution, but not means that HNSW itself is the best one. So it is the most well-known one, but not the best one. So from the pure algorithm perspective, so HNSW is mutable, which means that you can add data in it, and you can delete the data from it, and you can search about it. And some other immutable graph like Vamana and just before that, in case people don't know what is HNSW, HNSW is a graph data structure. So each vector will be a point or vertex inside the graph, and we connect this vectors with the edges, and you have multiple layers, and you can search, iterate upon this graph to get the closest one. And some other graph like Vamana from Diskin and NSG and this kind of thing, they are immutable, and also they have better performance. And also some quantizers can be applied on the HNSW or some other graph or other algorithms. And also if you change into GPU based, HNSW might not work because of GPU. GPU is totally different things. And we have Kagra, this kind of thing from NVIDIA. Now is supporting Milvus. This is super suitable for GPU. Also, HNSW is not good for BK. So graph-based algorithm actually not very good for BK. So if your K is a couple of thousands or 10,000 more, so graph can never satisfy your needs. And also, if you do a batch search, also graph is not a very good choice. So it is a general choice. So people always will not have that big K, will not have that big batch, and they don't need that super high performance, and they will not run a GPU, I think HNSW is a good start point. And also from some rich semantic features, HNSW also have some pure HNSW or some problems like filtering and sparse. You need to have some specific support on it. And from the use cases perspective, I have a concept called CAP in vector search. It's not about the distributor. It's about in vector search area. So it's a capacity, accuracy, and performance. So it's a triangle. You can never satisfy all of them. So only two of them can be satisfied. And HNSW is typically is accuracy and high performance one. And another two combinations can also have some use cases for the other two cases. For example, you want to have a very big capacity, very big storage capacity, and very accurate. So maybe choose some disk-based index like this. And also, if you want to have the performance and the capacity, you don't care about the accuracy. That can happen. So because people, some use cases, people can have a BK and search, get a result, and you throw them into the model to do a fine re-ranking. And in this case, they don't care about the accuracy. So like IVFS, QPQ, this kind of solution can be a great one.
That's a really great point. So I just want to reiterate to everybody. So just like with databases, we have these trade-offs. So the famous CAP theorem, where you just can't have it all. If your use case needs performance or availability, or P is what partitions, you have to make some choices, right? And it's really easy to make those choices based if you think about what your use cases are. And so there is a similar kind of triad with vector search as well. And once you kind of figure out, what is the most important thing? Is it accuracy? Is recall? Is it performance? Is it being able to search with that metadata, as Lee just mentioned? Understanding what those are, and then also not just choosing the database, but then choosing that index that's going to be able to match the requirements of your particular use case. And so HNSW is a great index, but just make sure that it matches what you're trying to accomplish.
Yeah.
Excellent. Okay, so it's vector database is a database, right? So, what about the ingestion side? Like, is there, what do we got to do on that side? What kind of preprocessing is required for a vector database?
Okay, so I have two interpretations on this. First is about people always asking, where does the vector come from? Where does the vector come from? And always you have a model, and you put your picture, you put your document into a model. It can be a bird, can be a OpenAI, whatever, large language model, this kind of thing. And you get this in vectors embeddings out and input into vector database. That looks like a very long, very tedious, very long run. Right? So, but luckily we have some tools to help. For example, Langchain and Llama Index, they are famous at it. So they can combine large language model, vector database, and the vector extraction, all these kind of things together. And also some of the vector database have already supported they include some large language model, not language, just some model inside their database, so they can do unstructured in and unstructured out. And some of them are not, so it depends. So it's about the first interpretation. So about how to do the ingestion preprocessing. Another one is if you mention about some pure vector streaming in and how we support these. My answer is so vector just get in and we search on it, and actually it's pretty hard to satisfy the data freshness and the data efficiency at the same time, which means that if you ingest data, you want to have the very high visibility, you want to search on it immediately. It depends on different kind of database. Some databases use HNSW directly, so they will when data get in, they will try to add this point to the HNSW graph. It takes time, and which means that you can now search what you just stream in immediately, and it takes some time. And this I call a sacrifice of freshness to reach the data efficiency. And inside Muse, what our design is, we have two layers. We will get it in, and we'll have a very fast building index to serve the data freshness. And then we have in background we build some graph based or some other immutable index to help serve the data efficiency. Yeah, that is. I'm not quite
Nice.
sure with that.
No, that
point.
was perfect. Yeah. So as you mentioned, so after people learn about vector databases, then their first question is, oh, how do I get those embeddings? So you can either use your own models to generate those embeddings and then insert them into a vector database. Some vector databases have the mechanism to actually create those vector embeddings. So look for that when you're choosing a vector database. You can also use other tools like LangChain or Llama Index, Semantic Kernel, etc., that have actually got really strong ties to a large language model, so they can also help you generate those embeddings before you store it in a vector database. So it all depends on what your use case is and what your stack is, but things for you to think about when you're choosing a vector database. Okay,
Yeah.
really cool. Okay. What about security? Because, these vectors look like nothing to me. I don't even know if I can decipher them. So why do I have to worry about security? Or maybe I don't.
I think always data security always matters, and no matter what kind of database you are. And since the vector database maybe it's hard understanding for you, but maybe it's easy to understand for large language model. Maybe in the future we have a magical interpreter that can understand it with some context on it. But in all these kind of cases, it's super important to have the security insurance inside the vector database. Also, and another point is beyond the vector data, we also have some structured data, which is a string, int. I mentioned the metadata. And we also need to keep the security of them. So features when it comes to what kind of security features. So first, the vector database need to need to get some security certification like SOC 2 from SOC 2, ISO, and GDPR, or this kind of thing. And another thing is about data security. Data security is about how you do data isolation, access control, the role-based access control, this kind of thing, and user authentication, authorization, and also cybersecurity is about some IP address control, access control, and private link into encryption in the transit, all this kind of thing. So this is another thing is I want to express a difference between face this kind of library and relatives. Just recall this question. So security definitely is one of it.
Yeah, you're absolutely right. So I was being a little facetious when I said, does it even matter? When you're choosing a vector database and you plan to put it into production, you're going to have to talk to your internal security teams. And, they don't know what vector embeddings are a lot of times still. And so you're going to have to explain what a vector embedding is. In their natural first reaction is going to be, oh, well, definitely somebody is going to be able to reverse engineer what that vector embedding is. And if there's any kind of company confidential information in there, they're going to be really, really concerned. And it's not something that's easy to do, but there are some papers out there that claim that they can do that kind of reverse engineering. So security is actually really important when it comes to your vector embedding, and your security teams will let you know that for sure. And then, as Lee mentioned, all the traditional security questions are going to come from your security teams anyways. So when you're looking for these vector databases, you're just going to have to put that on the list. It's going to be really critical when you're choosing your vector database. So we have a few minutes left, and I want to just go and get to some of the questions from the audience. So G. Lin asks, can you please share some examples of currently available vector databases?
Okay, so for some open sources one, Muse must be the most famous one, and Qdren and Vespa, and yeah, some this is what in my mind first class, and some lightweight one like Chroma and Lens, and some closed source one like Pantone, and also all these called, of course, based on the managed version of Milvus.
And then also, there's, every database that's out there, whether it's a NoSQL or a SQL-based database. I don't think there is a database out there that hasn't adopted a vector index. And so it is really important that everybody understand, what is a vector database. Our definition of a vector database is that it's purpose-built for vectors from the get-go. It supports a number of the features that we chatted about today. So not only does it support one or many vector indexes, but it supports the similarity metrics. It also handles the life cycle of vectors in a particular way. And then also, it's important to understand that trying to find those similar vectors is computationally heavy. And so vector databases will typically focus on trying to be very performant on that side of the equation. Whereas, some of the traditional databases, they were built for different purposes, right? So it may work in your situation, but just, go into eyes wide open and make sure that you articulate your use cases. Okay. Ollie asks, which LLM works the best with RAG currently, according to your opinion, Lee?
So this is a hard answer to hard question to answer. Since the LLM the model keep updating, right? So like we know recently the Cloud 3 did a great job on the benchmark, and GPT-4 is always a good choice. And also Llama is widely adopted in the open source. I don't think I have a very specific opinion.
Yeah, Ollie, sorry about that. Just keep in mind, there's a lot of LLMs that are out there. Of course, the most famous right now is, GPT-4 from OpenAI. Has a really simple API for you to interface with. Does come with a cost. So, if you're building something and it's not in production, you might want to look at, go to Hugging Face and look at the leaderboard there to see what other LLMs are there. There's some LLMs that can actually fit on your laptop, so you can just kind of prototype. Might want to consider downloading those. Or there's also a bunch of open source LLMs that might be sufficient. Once again, think about what's your use case and, and see, which model might be sufficient. So don't just go with the market leader. And then, unfortunately, as Lee mentioned, these models are changing constantly. So it's a race, isn't it?
Yes.
Every day it seems like, somebody new is coming out. I think Anthropic now has haiku support, and then a couple weeks ago, Voyage AI was talking about how they're really good with code, right? Because code is also very specific. So unfortunately, it's for all of us, it's it feels like a million people running by us constantly. So it's hard to catch up. It's hard to keep up. Okay, Vignesh asks, is a collection a set of vectors which could have one or more indices? Can you index the same set of data with different indices for different use cases?
So it depends on the different database, right? In Milvus, there's a collection is a concept in Milvus that is a set of not only about vectors, it's a table. As mentioned, you can treat it as a MySQL table, and one column is vectors from the latest from the vector Milvus 2.4. So you can have multiple columns of vectors and do hypersearch as mentioned on it, and you can index the same set of you can index the one column of vectors with one specific algorithm, AN algorithm, I think. Yeah. So it's from Milvus perspective. It depends on the vector database you choose.
Vignesh, but you bring up another good point that we didn't even think about. Yeah, even the word collection is very different from vector database to vector database. So you have to kind of dig into that to understand what does that especially mean. And I think you also have to ask yourself, what's your multi-tenancy requirements for your application? Because you can use these like collections or partition keys or a number of these things to help you with that. And so unfortunately, you're going to have to dig into that because nobody's using these terms consistently. Okay, so I want to go back to Armando had a comment question. So he wanted to know, can you do a hybrid search with 2 dense embeddings?
The answer is yes. Also depends on different kind of vector database. So from Milvus 2.4, we support it, so we can expect a release.
Yeah, I think I've seen like really, really intense workarounds to be able to do that from our users because it is definitely something that they want. With the next release of Milvus, we're allowing you in like a single row, a single entity, you can have multiple vectors that are you can store, so you can do a search against that. We're just trying to make things a lot easier. But even before implementing this, what we saw was people were trying to build that themselves, putting, doing these crazy
Couple
kind of queries, which
you can have it in couple collections.
yeah, you can have them in a couple. So it just is inefficient. So, back to
Yeah.
like, we're trying to make sure performance is still important. Let's do it so that you can get the best performance. Okay, so we did that. Abay, you had a really good comment earlier, and I do want to share with everybody. Our goal for today, after today's talk, is to turn this into a paper with lots of visuals. So for those of you that are more visual learners, we'll have a way for you to be able to grok this information via those means. And if you have other questions that you want Lee to answer, just shoot us a note. Lee obviously is passionate about vector databases, but also with his background, super passionate about databases in general. Probably coming from his time spent at Carnegie Mellon. You can also hear him speak at the Carnegie Mellon podcast. I think that was just maybe like 5 or 6 months ago. So where he goes really deep in the database side as well. Let me see if we have any last questions. Here we go. I have a very large collection in Milvus. I'll be performing either substructure or superstructure search. Should I drop index every time I perform a search or build 2 collections?
Can I ask what does it mean by substructure and superstructure search? So I'm not quite sure about the substructure and the superstructure search, the meaning behind it.
Yeah, so if you can give us a little more details, we can dig into that a little bit more. But hopefully we don't have to you don't have to do what you're asking, dropping indexes and all that. That sounds like just too intense for us. But let's do this. Shoot us an email. You can send me an email at chris.chirilla@zillis.com. You can ping us in the Discord channel. If you're listed as anonymous, so I wouldn't be able to respond back to you, but if you can send back a more detailed question, that would be cool. We'll try to get that answered. Let me just check one more time. Is there anything?
Oh, sorry. I think I had the answer. So it means you must have a binary things, right? You must have a binary vector. So it's kind of metric inside of binary data. And if you mean that you want to have 2 different kind of metrics, yeah, definitely. For now, you need to rebuild the data. You need to rebuild the index. And if you don't want to drop and rebuild it, and you definitely need to have 2 collections. Or from 2.4, you can have 2 columns.
So let us know. So it sounds like depending on what your situation is, if you're talking about binary vectors, or if you're talking about what we had mentioned earlier about having 2 vectors in a row, there might be 2 different answers here, but we need to get to what the question really is. All right, cool. Well, thank you, everybody. Like I mentioned, Sachi will post a recording as quick as she can. She's going to do a quick edit. If you have any other questions for Lee, you can reach him in our Discord channel. You can also reach him in our in GitHub, in the GitHub discussions area. And also, if you have, we will create this into a paper with lots of visuals to make this even more clear. And if you even have more questions, what we can do is we can always do a follow-up webinar with in whatever format you like. So if everybody likes this kind of a format where we just do a Q&A, we can do this again. Or if you prefer more traditional webinar style, we can do that. We wanted to try something a little different this time. So let us know what works best for you in your learnings. And we hope that this information helps you to decide what are your requirements for vector databases, and whatever vector database you choose to match your requirements, we hope that you are very successful in the cool things that you're building. Any last words, Lee?
No, I'm so glad to share all these kind of things with you, and actually I have way more words to say, but it looks like I don't have any time now, so hopefully I will have time. Yeah.
All right. Thanks, everybody. We'll see you guys again soon. Bye-bye.